Okay, thanks for the introduction, Per. My name is Max, this is Blase, and together we present joint work with our colleagues Alex, Amanda, and David. And in this work, we describe a new technique that we developed to reason scientifically about real-world password cracking software. Well, I guess everyone here knows that sometimes people choose weak passwords, and you might ask what makes a password weak. And there's something called a selection bias. And a selection bias means that passwords are not uniformly distributed, but instead they are somewhat shifted and there are more frequent passwords. It simply means that there are some passwords that are more popular than others. And yeah, well, attackers are aware of this. And what they do is they guess the most common passwords first. So they adapted their guessing strategy. Here's an example. Imagine the password 123456. It's one of the most common passwords. And what is happening here, it's often the first guess that attackers make when they try to crack passwords. And in academia, we use exactly this information, how many guesses have been made, to reason about the strength of a password. And we simply call this number the guess number. So at a high level, it's the number of guesses required to guess a password. And it's usually a good indicator for how strong a password is. And it has some applications, the more tiny bar, password strength meter, and here the guess number is used to show in a tiny bar or as text how strong the password is for the user, and they can use this information to choose better passwords. Another application are so-called proactive password checking. Imagine a user tries to make a password, the password is sent to the server, but before the server stores it and hashes it and saves it in a database, the server checks the password whether it's reasonable. It looks like this. There's a grumpy pear sitting in your server and telling you, hey, your password is weak, you cannot use this. Right? Another application is research, and that's why we mention it here. We try to study how users' mental models are, and we want to evaluate a new scheme for helping people create a better password. And then we ask the question, well, did the person create a better password or a worse password? And we can use the guess number here to reason about this. So I guess everyone has understood what the guess number is and why it's so useful, but I haven't fully defined them. A guess number is calculated for a specific attack using a specific algorithm with a specific configuration. So the guess number highly depends, for example, on the input data, the password leak you're using. And this makes it very different to what the normal password cracking community is interested in cracking, simply cracking the password. We defined some goals for guess numbers. We want them to have 3 properties. The first one is the process must be efficient. The second one is we want to have a systematic approach to configure the password guessing attack. So based on a large file of plain text passwords as input. And finally, we want the attack to be real. So the guess number or approximation of the guess number should be based on real-world data. And yeah, since the guess number depends highly on the attack you execute and the model behind that, I want to introduce you to the state-of-the-art in password cracking. I guess some of you already know this, but there are 2 main classes of password cracking methods. The first one are probabilistic algorithms or models, and the second one are software tools like John the Ripper, and they are used in the InfoSec community, and I guess by many people here in this room too. So let us start with the probabilistic models. They are very popular among those people that went to school for too long, right? There we have Markov models, probabilistic context-free grammars. You know them as PCFGs and neural networks. And 2 of which were created by people here in this room, so we can be very proud of that. And with those models, we already know how to calculate the guess number very efficiently, very fastly. And there's a paper from 2015, and they propose to use the algorithm to estimate the guess number without actually running or enumerating the algorithm. But of course, the guess number depends on the configuration, and here again, the probabilistic models have the advantage that it's already built in. So given some training data, the probabilistic algorithms mostly configure themselves. But there's a real problem with them because they are not used by the InfoSec community. Professionals don't use probabilistic models, and the reason for that is simple. Their wall clock time for guessing passwords is very slow. So there's no straightforward way to implement those models on GPUs, for example. That's why they are not used. But what do they use? Well, I mentioned it before, the software tools on the right, John the Ripper and Hashcat. And what does those tools do? They perturb passwords. So they change a password in a way a human would when creating a new password. And I will explain it later how it works. But to get the guess number here is you need to enumerate. You need to run the algorithm, generate guesses, and then once you have the guess or the password that you're searched for, you get the guess number out of it. And it's not very efficient if you need to do a lot of guesses. So for 6, it might be fine, but it's definitely not fine if you need to have a quadrillion number of guesses, which is 10 to the power of 15. So the approach does not scale. And we have a very inefficient process, and this makes it also difficult with the configuration, because every time you change something, you need to wait for a very long time. You need to wait several hours to get the configuration out, the result out, and check whether the configuration is successful or beneficial or whatever. But there's an advantage. The tools are used in practice. That's why they're interesting for us. And now we have built new tools, and with those new tools, we can reason scientifically about those real-world password cracking software, and that's what we try to explain today, what we did here. Before Blase explains the approach in more detail, let me quickly introduce you how those software tools like Hashcat, John the Ripper work. And they have different attack types, but the most common one is the mangled word list attack. And what happens here is it's a rule-based attack. You have 2 inputs. The first one is a word list. It's very simple. It's simply created of leaked passwords or a password list. And the second one is a rule list. And the rule list is then applied to the word list, and it outputs a stream of guesses. Here's an example. We have the password super. The rule is append 1. So the first guess is super 1. And then we take the second password in the word list, apply the same rule, and then we get the second guess, password 1. And this continues, and after we have done this for all passwords in the word list, we apply the second rule in the rule list. And then we move on until every password and every rule has been applied. So you might wonder, how does such a word and rule list look like in practice? A word list can have 60 million passwords, up to 500 million passwords. They can be bigger or smaller. And a rule list, well, there's one that has 64 rules, one with 5,000 rules, and one with 65,000 rules. It could be more. If you do the math behind it, you will see that you have, at the very end, a trillion or a billion, a quadrillion of guesses. It's a very large number. And that's here the problem, that if you enumerate, it's not very efficient to do. And there is some evidence that professionals like Cynosure Prime, Team Hashcat, John users, they have their own private word and rule lists that are more efficient. And for us academics, it's rather complicated to catch up with them. And that's the real problem here. That's why we're very fortunate that our new tool allows that, or makes it easier to solve this problem. And Blase will describe how we do it.
Great. Thanks, Max. All right, so now I'll walk you through our techniques for basically reasoning analytically to get guess numbers. Right, so the problem setting is we start off with some password of interest, like Chick4Go. Right, so what I'm curious about, I'm like, given this password, how easy or hard is it to guess? Right, and so normally, as Max presented, when we're thinking about these tools, we're thinking in this what we can call the forward direction. That is, we take some word on the word list, like Chicago, put it through some rule, like replace A's with 4's, and then we get our guess Chick4Go. Right, and so the way we're going to do this analytically is by reasoning in the backwards direction. Right, and so this is actually a pretty old idea in the community. So people have called it like rule reversal, so on and so forth. So if you go back to kind of the ancient history of PasswordsCon, it was mentioned as a main part of the talk in passing in lots of talks many years ago. right? And so what we did is we actually kind of took this idea, ran with it, and tried to work out a lot of the details, which turned out to be way more interesting than we had expected. Right, so let me walk you through this, this kind of process of working backwards or inverting the attack. Right, so we have our password, Chick4Go, right, and so now we want to work backwards. So we say the first thing on the rule list is append 1. Right, so what's working backwards from appending 1? Well, it's going to find the 1 at the end of the password and getting rid of it. Right, so we take Chick4Go, look for the 1 at the end, try to get rid of it. Alas, there is no 1 at the end. So no matter what's in the word list, it could be a billion entries. No matter what's there, it's not going to guess Chick4Go. So we say, we don't even have to reason anymore about this rule. Like, thank you, next. Right. So now we say this next one: replace A's with 4s. How do we work backwards from that? You get Chick4Go. The word list for Chick4Go, where if you replace A's with 4s, you get Chick4Go. Right. And so here there are actually two different things. Chicago with an A, the A would turn into a 4. Or if you started with Chick4Go, there are no A's, so it just stays the same. Right? So in essence, there are two things in the word list in which we can call preimages that, if they're there, means this rule will guess this password Chick4Go. Right? And so what we can do is just say, have an efficient representation in memory of our word list, like a hash table, where we say, like, let's look up this, are they there? Yes, the password's going to be guessed. No, it won't be guessed. Right? And so we don't actually have to make any guesses. All right, and so we can determine which rule, if any, guesses the password. So now we just have to say, well, how many guesses did it take to get to it? Right. So if kind of thinking in the John the Ripper style of enumerating guesses, and I'll come back to this because it's an interesting subtlety. Right. So we can say, well, this first rule here, let's say if we have in this toy example 3 entries on our word list, makes 1 guess per entry on the word list. So we make 3 guesses. So we just know without making these guesses, 3 guesses would have been made. It didn't guess it, so we move on. This next time, this next rule also made 3 guesses. So we have bounds. Our guess number is somewhere between 4 and 6, right? And we can estimate it more tightly based on where this position of the word of interest was in the word list. Right. So in other words, what we're describing is you have this password where you want to get the guess number. You invert it for each rule going down the list, right? And you identify the first rule that would guess it, along with the words of interest, right? So then you can just sum the guesses in the John style made by the previous rules, right? So how do you sum the guesses? You have to go through this process of counting rules. Right, and the subtlety here is that John the Ripper and Hashcat enumerate guesses actually in a different order. It's basically the opposite loop. Right, so John iterates, for each rule, takes all the words, makes those guesses. Hashcat conceptually is looping over the words, applying the rules to them. It's actually it's a much more interesting and really cool batching strategy for performance. Right, and so what we do is we just reason about this, but we only have to do this once. We can pre-process this if we don't change the word list or the rule list. We've done this once. Any password that comes in, we already know how many guesses each rule is going to make. Right, so I mentioned this is kind of an old idea of rule reversal. So what turned out to make this hard? And I learned this was hard because a student at Chicago came to join the group. I said, oh, I have this kind of idea that's been floating around the community for a while. Let's implement this. It'll take a couple of weeks. And then 2 years later, we finally finished. Right. Okay. So one thing is that we want to be able to handle any rule that comes our way, or almost any rule that comes our way. Right. And so a rule is basically a combination or composition of transformations. Right. And to capture the way, as Max said, that humans might perturb a password, there are dozens and dozens of different transformations you can make, and some of them take input parameters, and so there's a huge space of things that can do, and they introduce actually really complex dependencies, and I'll show some examples in a moment. Right? Okay, so let's say we'll keep with our password of interest, Chick4Go. Right, and so what we're going to do is represent the set of possible preimages as more or less a regular expression, regex. Right, so in the example I showed before, where there were 2 possible preimages, we said a bunch of these characters are fixed. In one place, there could have been an A or a 4. Right, so here we had 2 preimages. We looked it up in a hash table in memory, and that was super fast. Right, of course, it's not that easy, because sometimes you get these passwords like 4444 is your password of interest. And so each thing, each character could have started off as an A or a 4, so there's 2 to the 4. If pairs making your password composition policy, you have to have at least 15, 2 to the 15, so now we're actually talking like real numbers. This is, looking things up in a hash table maybe is not going to work. Right? And you actually find a similar phenomenon, not just for idiosyncratic passwords, but actually sometimes for whole classes of rules. So if you have a rule that somewhere among the transformations says, let's just purge all of the 1s and get rid of them, and when we're reversing this, we say, well, there could be 0 or more 1s basically anywhere in the password, right? So we have to reason about that. And so what we do is, if there are a small number of possible pre-images, we look these up in a hash table. If there are a large number of pre-images, what we do is we've represented the word list as a trie. So it's basically a tree with prefixes. And the reason this works is that there are lots and lots and lots of possible passwords. They're all sharing these prefixes. Most of these, as you start going the first few characters, you realize there's no password, or sorry, there's nothing in the word list with that prefix, so you've basically pruned a huge part of the space, right? And so representing it as a trie actually worked, in these kinds of examples where there otherwise would be lots of things to look up, right? So counting guesses also turns out to be hard, right? So I mentioned before this in the toy example, each thing on the word list made 1 guess. Right, but it's not always that simple. Sometimes it's like each thing for John, on the word list can make 10 guesses, right? But then you can also have, what are called rejection rules. And so you might want to say, if I'm replacing A's with 4s, it doesn't really make all that much sense to replace an A with a 4 if there's no A in the word, because then nothing changes, right? So I might say, when I read the word in, if there's no A, skip the guess. It's not worth it. Right, so now we have this dependency, oh, well, the number of guesses made is not the number of reasoning about that. It's the number of things on your word list that have an A. Okay, we can start reasoning about that. Right, but it gets more complicated because these rejection clauses can come anywhere in the set of transformations. So we might say, oh, replace E's with A's, then check if there's an A, and if not, don't make a guess. Right, so now we have this dependency that anything with an E or an A in the word list, we'll make a guess. And then you have some transformations, for instance, that are adding characters, removing characters from the password, and then you might have a rejection rule based on length. So you have to reason about how many things, once transformed in all these different ways, are still going to result in a valid guess. Right, and so the way we do this is we make a first pass through the rule list and say, what are all the dependencies in this rule list that are going to come up? What characteristics of the things on the word list are going to matter? And then we represent basically, we have a tensor representation for all these different things on the word list, so we can then make one pass through the word list, then with this representation, then go back and say, oh, we're interested in how many passwords are at least length 6 with an E and an A, and we just look that up. Right, so this lets us go kind of count the guesses quickly, making only a single pass through the word list. Right, and so all these kinds of these tricks where we're kind of skipping steps by reasoning analytically about things are how this becomes an efficient process. Right, so I've just explained this process. When is it useful and when is it not useful? Right, so this method is preferable basically when you have a small number of passwords of interest, and small meaning on the orders of thousands, tens of thousands, sometimes hundreds of thousands, right? And you need guess numbers quickly. So if someone gives you a password and you need to say in a second, is this a good password or a bad password? What's the guess number, right? It's not preferable if you have a billion passwords of interest, the cost savings you get for each step looking up each password don't make sense. So in that case, it actually makes more sense to run the attack in the forward direction and kind of look up which of these billion passwords are guessed on each step. Right, so let me just give you some performance measurements, and we didn't try to optimize our code all that much, but it'll give you a sense of where we're getting this efficiency. So if you're doing an attack, modeling an attack, using John the Ripper, let's say if you take all the uniques from the LinkedIn leak, like 60 million or so, as your word list, take this list originally put out by CoreLogic for Crack Me If You Can a number of years ago, reordered by someone from Spider Labs for guessing efficiency. This is making 3 times 10 to the 14 guesses, so 300 trillion, right? So if you were to try and enumerate this and write it all to disk, uncompressed, writing 300 trillion guesses to disk would take about 3 petabytes. And so I don't have 3 petabytes of disk, unfortunately, so we didn't try to do this. So our approach with our bytes, so basically we do this pre-processing, kind of build these different representations, we end up with about 10 gigabytes of auxiliary data. So there you have many, many orders of magnitude improvement. Right, so how long would it take? So we did some micro benchmarks of John writing to standard out, then writing to disk. This would have taken us over 2 years to write to disk, so we didn't do that. Our approach actually just takes a couple of hours, so much less than a day of pre-processing. Right, so we do that once, right? And so then the question is, how long does it take per password? Right, so if we had enumerated it, we have these 3 petabytes in disk, we'd have to go sort 3 petabytes, which is unpleasant, right? And then you could do a binary search each time, which takes a little bit of time, right? But sorting 3 petabytes, I'm not going to do that, right? So in our approach, we found that for almost all passwords, you get the guessed number in less than a second. Right, and of course, passwords that aren't guessed in the attack are going to take longer because you have to go through everything, whereas you basically short circuit if you find something that would guess it. All right, so I've talked you through kind of how this idea works for guess numbers, but Max also mentioned that the configuration matters. And so with these probabilistic methods, we have this nice property that we throw data at the problem, and modulo having to adjust some parameters, the approach figures it out from the data, figures out your model of passwords from the data. So can we do something similar for like Hashcat and John? Right, so the attack is going to depend on a couple of things for these tools. First is what's in your word list, and next is what's the order of the things in your word list. Next is what's in the rule list, as well as, you might guess, what is the order of the rule list, right? So let me take you through 2 examples of these, right? So broadly, as I said, we want this data-driven configuration. Like you take the starting point of your word list, starting point of your rule list, and then some leaked passwords, this is basically training data. Throw it into a blender, or our approach, right, and say what should come out is this new configuration that ideally works better, right? And again, we want to do this without actually making any guesses. Right, so I'll take you through how we can think about reordering the rules, as well as expanding the word list using kind of these methods. Right, so reordering the rule list says, should the rules be in a different order? Right, and this, of course, isn't going to change what's guessed. It's just going to change how quickly in the attack things are guessed. And you might use that information you're getting more quickly to adjust what you're doing. And you could imagine situations where you adapt your attack if you guess more quickly. Right, and so the key idea, and this goes again to prior work from, in fact, PasswordsCon, is you can say, let's reorder the rules based on the ratio of the number of successful guesses to how many guesses it's making. So it's basically the success ratio. Right, and so I'll show you a graph here of what this looks like. So on the x-axis, we have the total number of guesses made. We have the percentage of parameterized attack in a logarithmic scale. And on the y-axis, we have the percentage of passwords cracked at that point in the attack. Right, and so this is taking modeling a John attack. This rule list from Spider Labs, and I believe it was the word list from LinkedIn. Right, so this is kind of the original ordering. And we said, let's say for some target data set, some leak, we knew all the answers, and we could say we can't change the contents of the word list or rule list. We can't change the order of the rules. All we can do is reorder the rules. How well could we do? As I mentioned, it's not going to change what's guessed. It'll just change how quickly we guess things. Right, so this dotted red line is the ideal if you knew all of the answers and reordered based on that. Then we said, well, what if you took some other leaked data set, reordered the rules based on that, and then applied it to this other, this original leaked set? So you're using data from other leaks, reordering the rules empirically. How does that work? And so it turns out if the leaks were created under similar password composition policies, it works actually pretty close to the ideal. Right, so you reorder things, and we said, we're not quite ideal with the ordering of the rules, but we're pretty close. And again, the caveat is they have to be of a similar composition policy. All right, so we can reorder rules, and again, we don't have to make any guesses. We just reason about this. The guess numbers for each, which things in our password set, which rules would guess them, and then we can reorder based on that. Right. So I'll quickly take you through kind of the last part, which is what we call word completeness, which is should other things be in the word list? Right. And so the idea is from before is we say, well, we're reversing things, looking things up in the word list. If there's some things we keep looking up and they're not there, what you could call a cache misses, well, maybe they should be there. Right. And so at a high level, our method says, well, let's, you get some new password set. Dagarna1, Dagarna with a bunch of @ signs instead of A's, Dagarna lowercase, and right, you're basically looking backwards and saying, well, all of this is coming from the same preimage. So if we had just added that one thing to the word list, we would have been guessing better. We would have cracked more things. Right. So what we did is we applied this to a bunch of leaked data sets to see what would come out. Right. So one thing that was coming out, for instance, we threw the Battlefield Heroes set at it, Neopets, things, and this is just a kind of a sanity check. Things that were coming out were like BF Heroes spelled wrong, I love my Neopets, right? So this is a sanity check because a good attacker would have known, oh, I'll put these things in my word list to begin with, right? But so sensible things were coming out, right? But lots of things you wouldn't have thought to put in the word list were coming out too. We found a huge set of meaningful things like la la la, like I'm trying to make a password, what should it be, la la la. Well, we hadn't thought to put that in our word list. We hadn't seen that before in the sets we trained on. A bunch of short strings were popping out too, because when combined otherwise. Rules, it turns out those were actually they were guessing a bunch of things that were not going to be guessed otherwise. Right, and so in other words, we're thinking about this working backwards and saying, these pre-images we're looking up that aren't in the word list, well, let's put them there if they're coming up enough. Right, so what Max and I have presented on behalf of our colleagues is that we've thought about how do you reason about these real-world password cracking tools analytically, and then certain kinds of applications that are useful in academia, this is really useful for us because we can now get guess numbers from passwords efficiently. We can also reason kind of in this data-driven way about the configuration of these tools. Right, and so our students wrote this research quality code. We posted it, open sourced it. It's not made for performance. It's written in Python. Right, so if you're interested in these ideas, would love to talk. And both Max and I would be happy to take questions right now. So thank you.